Hello, we're back with the third part of the 2009 PAT, so the slightly longer written physics questions. Question 23, a hot object will glow emitting radiation with a total power approximately given by this relationship here, where A is the surface area, T is the temperature, and K is the Stefan Boltzmann constant. Estimate the surface area of the filament of a 75-watt incandescent light bulb working at 5,000 degrees. Right, so we want to get A out of all of this. So we want to have A is equal to P divided by KT to the power of 4. So that is 75 divided by, we got various bits going on here. So T to the power of 4. So we've got 5 to the power of 4, so well 25 squared, but we've got this 10 to the 3, so that's going to give us a 10 to the minus 12 up here. And then we've got the Stefan Boltzmann, which is 6 at the bottom and a 10 to the 8 at the top. So we just need to figure all of this out. So that's going to be 325s going to 75. Divide that by 6 gives a half, so we'll have 1 over 50 for all of that, times 10 to the minus 4. So 1 over 50 is 0.02. So we'll have 2 times 10 to the minus 6 meters squared. That's what we're working in, is it? Yeah, we're going for a surface area and we got meters all the way through it. So that's just a case of pushing some numbers around in that question. And we got question 24. Oh, here we go again. So yeah, we got more of this simultaneous equation stuff. Freight transport on Titan is mostly by ship. 3 types of ship called Pangs, Quizzers, and Roodles. Yeah, P's, Q's, and R's. All 3 ships have the same shape and design, but differ in size. Right, so we're going to have all this proportion stuff, I'd imagine, on this. Cargo capacity depends on the volume. So capacity is proportional to volume. We've got number of crew proportional to the area. Quizzer and a Roodle of the same length as 2 Pangs. So Q plus R equals 2P. Crew of a Quizzer is just sufficient to provide crew for 2 Pangs and a Roodle. So the crew of a Quizzer, and the crew is proportional to area, so Q squared is what? 2 Pangs squared plus a Roodle plus an R squared. Okay. Wonderful. So I suppose we're just going to have to do a bit of a substitution on all of this. So let's get rid of Q, should we? Seems like a reasonable thing to do. So Q is 2P minus R. So that, when we square it, is going to be 4P squared plus R squared minus 4PR. Just substituting in here for Q. So we've got 2P squared is, the R squareds have cancelled, is equal to 4PR. So P is equal to 2R. That's good. So that's going to tell us about Q then. If P is 2R, then Q is going to be equal to 3R. Okay, so what are we wanting to do now? The fully loaded Quizzer wishes to transfer all its cargo to smaller Pangs and Roodles while minimizing the number of crew required. How many Pangs and Roodles are needed? And we got the usual hint at the bottom there that they always give us of this stuff to do with areas and volumes, so we sort of already dealt with that. Okay, so we've got, what are we doing? We've got a fully loaded Quizzer, so we've got something to do with Q cubed, because that's going to be to do with the volume of that. Wants to transfer all its cargo to Pangs and Roodles. So that's going to go to some number of Pangs, so let's say alpha P cubed plus beta R cubed. So we've got some kind of split on these where that's the number of Pangs and that's the number of Roodles. And we need to do that while minimizing the amount of crew. Right, okay, so we need to minimize, so the amount of crew is going to be alpha p squared plus beta r squared. So we need to keep that to a minimum, right? Right, terrific. So, oh, but we can get that in terms of one thing because we've got p is 2r, so that's going to help matters, isn't it? So that's going to be alpha times 4r squared, so 4 alpha r squared plus beta r squared. Right, so we need to keep that to a minimum. So what we do, well, we do another substitution in these, I suppose, in order to get everything in r's, and then, yeah, so let's sub in here. So that's going to be 27r cubed, sub in for q, p cubed, so that's going to be 8 alpha r cubed plus beta r cubed. So we can cancel all the r cubes, and we've got a relationship here between alpha and beta. This is going to give us some options of what we can do. So we could have, so let's say alpha, beta. So if alpha was 0, so we didn't have any, whatever the alphas were, any pangs, so we had no pangs at all, then we'd have to have 27 Rudels, because this thing's got to add up. Yep, so beta would have to be 27. If that was 1, then we'd have 19. Is that right? Yep, we'd have 19. 8 and 19 is 27. If alpha was 2, we'd have 16 there, so we'd have to have 11. If alpha was 3, we'd have 24, so we'd have 3. So we can't have any more than 3 of those pangs, otherwise we'd already be over capacity. Actually, well, it doesn't say you transfer, minimize it. Well, you could go beyond, because you could have some empty ship, I suppose. I didn't say you can't have empty ship. So if we had 4, we'd have 0 there. I don't see anything about you can't. Yeah, we just have spare capacity on the 4 pangs that we've got. Right, so we need to now look at, let's see if we got some kind of trend here in crew. So our crew that we've got on this is we need to minimize 4 alpha plus beta. That's what we need to keep to a minimum. So let's add 4 alpha plus beta onto here. So that'll be 27 for the first one. Then we'll have 4 plus 19 is 23, right? So it's dropping. 8 plus 11 is 19. 12 plus 3 is 15. And then we're going back up to 16. All right, so that's good. So we have gone back up again, and it will keep on increasing. Like if we went 50, obviously that's doing us no good. It just goes up to 20. So we have got a minimum here on crew. So we need 3 pangs and 3 Rudels in order to, yeah, satisfy both the load from the quizzer and the minimum crew. That was actually a relatively interesting one, considering maybe they were getting equally bored of these simultaneous equation ones in the previous papers. And I mean, this has got something to get your teeth into at least. So I don't mind that one compared to what I was expecting. So question 25, we've got 5 identical 1 kiloohm resistors arranged in a network as shown. First of all, what resistance would be measured between terminals A and B? Right, so when we're doing these networks, you normally want to start on the inside and work out. So let's start with these 3 here in parallel. So if we've got 2 at the bottom and 1 at the top, so we're going to have a half plus 1 is 3/2 and then flip it 2/3. So I'm just working in multiples of R. We're putting in 1 kiloohm later. So we've got 2/3 for that block. We've got 1 for that, and we've got 1 for this. So at the bottom, we've now got 5/3 because they're in series. Now we have to do in parallel with the one at the top. So that'll be 3/5 plus 5/5 is 8/5, and then flip it. So 5/8. So we're going to have 5/8 times 1,000, which is 525s, which is 625 ohms. So that's all relatively straightforward. If a 6-volt battery of internal resistance 125 ohms is connected across terminals A and B, what current flows between C and D? Right, so we're sticking in this with an internal resistance across there. So that's 125 ohms, that's 6 volts. And we want that current there between C and D. Right, there's a couple of ways you can do these. I think I might do this twice because I like these sort of questions. So let's start with the maybe more standard approach of looking at PDs, and we'll just break down the potential differences as we go around. So potential difference breaks down in proportion to resistance as we're splitting it around the circuit. So we know we've got 625 ohms, which we already know is 5 times 125, and then we got 1 times 125 down the bottom. So the split between this 125 and then this 625, you're going to have 1 volt going across this, and we're going to have 1 volt, and we're going to have 5 volts going across all of this. So we've got 5 volts across there. Now let's split up what's going on in these. So we can split that 5 volts in proportion. We've got a 1 to a 2/3. So we've got 3 to 2 is our proportion from here to there. So we must have 2 volts going across this set of 3 resistors. So we've got 2 volts with this resistance of 2. We're now, just looking at what's going on that wire from C to D by breaking it down that way. So yeah, that's now straightforward. We've got I is V over R. Our voltage is 2, our resistance is 2000, so we've got 1 milliamp. So that's doing the more standard potential difference approach. Maybe let's look then at how we could do this with current. I'll change over color. Nice trying something different here. So our total current, we were going to start off, let's go for total current. That is going to be equal to 6 divided by 750. So that's talking about our maximum current as we turn up here at A. Say we've got that going on. So that is 1 over 125 amps, which is going to be 8 milliamps. That's what we're playing around with. So now let's see, we've got to go through 2 junctions to see what's happening with this current. So now we've got the reverse of what's happening. The current is going to mostly go where the resistance is lower. So when we were looking at this split that we had before, we had 5/8 versus 3/8 is what we had on our split when we were comparing these things, because we got a proportion of 1 versus 5 over 3 is what we had in all of this. So we've got 3 over 3 to 5 over 3. That's our proportion that we've got going on. So we've got 8 things, 3 plus 5. And it's going to go in the reverse of the resistance, unlike the PD, which goes with the resistance. So we're going to have 5/8 of the current go up through the 1 resistor, and 3/8 of the current go down to the bottom. So we've already got 3/8 there. So at that point, we've now got 8 times 3/8 working in milliamps. Now we get to this split here, and we're going to have 2/3 of it go upwards, because that's 1, versus 1/3 of it going downwards, because that's 2. So again, we're doing the reverse of the split. So we're now only taking 1/3 of what's available at this point. So now we've got 1/3, and that's going to be our final current that's going through C and D. Cancel the 8s, cancel the 3s, 1 milliamp. So it is the same process really of doing this with the potential differences, but whereas potential difference is proportional to, written that the wrong way around, potential difference is proportional to the resistance, the current is inversely proportional to the resistance. So you just have to flick things around the other way. But again, everything is split in proportion. So you just need to be careful of what's going on with all your proportions around the circuit. and then just work your way round. Think what happens to each junction. I quite like this current approach because it really gets you thinking about what the current's doing every time you hit a choice. Okay, it's going to follow the low. Most of it's going to go the way of low resistance, but you're still going to have some going the other way, and it splits in that inverse proportion. So yeah, I love those sort of questions. The circuit ones, they're probably, yeah, I think they probably are my favourites out of all of the ones I have in these. Right, let's push on anyway. Get carried away on all of that. That's question 26. So this is our last one. So we've got an electron gun in a cathode ray tube accelerating an electron with mass m, charge E or minus E across a potential difference of 50 volts, directs it horizontally towards a fluorescent screen 0.4 meters away. How far does the electron fall in its journey to the screen? Right, so we've got some electron gets accelerated through this 50 volts, then it pings out towards some screen 0.4 meters, but it's going to just sort of drop off a little bit, not by a lot though. So we need to get the energy, so the half mv squared, because all the energy that we're getting in this acceleration is going into kinetic energy. That's going to be equal to the joules per coulomb multiplied by the coulombs, because that's what happens with moving charged particles through a voltage. M was 10 to the minus 30, so V squared is going to be 100 times 1.6 times 10 to the minus 19, so that gives us that. And then we have to multiply by 10 to the 30, and then we need to square root it. So V is going to be, that's 10 to the minus 13. So let's borrow one of those and say 16 times 10 to the minus, 10 to the plus 13, I should say. And then we'll borrow one to make that 10 to the 12, because then it makes it easier to square root it, because you can just say it's 4 times 10 to the 6 then. So that's good. That's our meters per second that we've got. So we've got then that the time to the screen is going to be distance over velocity. So 0.4 divided by 4 times 10 to the 6. So that is going to be 10 to the minus 7 seconds. So we need, it's going to gain, in 10 to the minus 7 seconds, it's going to gain vertical velocity of that times g. Gain of vertical velocity is 10 to the minus 6 meters per second. So our vertical drop is going to be our average velocity times the time. Average velocity multiplied by time, which is 10 to the minus 6 over 2. That's our average velocity times the time, which is 10 to the minus 7. So we've got 5 times 10 to the minus 14 meters. So surprise, surprise, is not very big, but that's what we'd expect. So yeah, that's just, mixing in various simple stuff to do with what does a potential difference actually mean. Your volts or joules per coulomb multiplied by the coulombs, and we got some joules that goes into kinetic energy, and then a basic projectiles question. I would recommend not jumping into SUVAT all the time. It's so trivial doing these sort of things, working out that your time to screen, if you've got your velocity equals distance over time, then why not use that in order to get time is distance over velocity, which we're doing there. Your gain in vertical velocity, this is accumulation of acceleration, as I keep on going on about on these things. Your acceleration multiplied by your time is your accumulation of velocity. It's the amount of velocity has changed. That's your delta V. So if you're starting with no vertical velocity, as we are here, because it's coming in horizontally, then just use that. I know it's exactly the same as V equals U plus AT, where U is equal to 0, but talking through it in this way and having your change in the velocity, you know, v minus u is a times t, I think is a much better way of writing out that formula because you're getting used to the fact that that's what it is. Your accumulation of velocity, accumulation of acceleration, I should say, is your change in velocity. Same here. Your distance traveled is average velocity times time. Just use that. Don't keep jumping into SUVAT all the time. I mean, I know all of these things have got SUVAT equations associated with them, but learning how to articulate these things and just talk through it makes it so much easier to grasp. It's so much more logical. It's so much easier to communicate to other people. Conceptually, it's just got a much firmer foundation, and you will be grateful for it later on when your understanding of all of this is just so much deeper. So don't rush into SUVAT. I think the only time I really have any sympathy for the SUVAT stuff is when we're using the S equals ut plus a half at squared, because we've got information on S and A, but we don't have the velocity bit. And although you can build this up and you can take your acceleration and put it into something to do with velocity, and then take that again and put it into the displacement, or vice versa, you end up at that equation and you're sort of manufacturing it. So sometimes there is something to be said for this one. If you're doing the other ones, if you've got V and A or you've got V and S, then just don't SUVAT it. Seriously, just waste the time. Anyway, that's a nice set of questions. We've just got the long question to go, and then that's 2009 done.